Hello everyone, this is lecture 11, Properties of Determinants. So the learning objective of this lecture is to find the determinant of a matrix product and a scalar multiple of a matrix. We're going to have a formula for this type of determinant of matrix. Then we find the determinant of an inverse matrix and recognize the equivalent conditions for a non-singular matrix. And later we're going to find the determinant of the transpose of a matrix. And before we write down the formula for matrix product and the determinant of matrix product and the determinant of scalar multiples, we're gonna follow we're gonna do some example. So I have these two matrices here. A is equal to 1, -2, 2, 0, 3, 2, 1, 0, 1. And the second matrix is 2, 0, 1, 0, -1, -2, 3, 1, -2. We're going to calculate the determinant of A, the determinant of matrix B, and the determinant of the product A times B. Okay. So in lecture 9, we learned how to calculate the determinant of a matrix, right? Well, we're going to calculate the minors and cofactors. In lecture 10, we observe another way to the calculation of determinant based on the elementary row operations. Okay, but for this lecture, we can just focus on the technique that we learned in lecture 9. Okay. So if to calculate the determinant of matrix A, what you do is you just solely choose one of the row or column to work with. So this the 3 by 3 determinant. I'm going to choose the last row. You know what? Choose the first column to work with. So it's easy enough, right? So for the first column, right? It should be a 1, 1 times C 1, 1 plus A 1, 2 times C, sorry, C A 2, 1 times C 2, 1 plus A 3, 1 times C 3, 1. Okay. So C1, 1 and C2, 1, C3, 1 depends on the sign of the minors, right? So for C11, the entry is positive, right? For C21, the entry is negative, and C31 is the entry going to be positive again. So A, or the determinant of A is going to be a 1, 1 times M11 minus A21 times M21 plus A31 times M31. All right, so A11, you have that is equal to 1 times M11. So you choose the first entry here, delete the corresponding row, and delete the corresponding column, and you get M11 to be 3, 2, 0, 1. For these calculations, A21 is equal to 0, so automatically you can say this is equal to 0. For A31, right, so you choose A31, you delete the corresponding row or column and the corresponding row, and you're left with the determinant of the form, so plus 1 times the determinant of the form, right, -2, 2, 3, 2. Right, so we got this is equal to 1 times 3 plus 1 times -4 minus 6. So together we have this is equal to -7. So that is the determinant of A. Now for the determinant of B, so let me just write down the formula on the result only and let me get rid of this calculations. Right, so -7 is the answer for the determinant of A. Now for the determinant of B, you want to calculate 2, 0, 1, 0, -1, -2. 3, 1, negative 2. All right. So again, you're going to choose the first column to work with. Let's choose the first row to work with and see what happened. So A11 times C11 minus A12 times C12 plus A13 times C13. And here A12 is equal to 0 as well. So we can just let this term go to 0. Now A11 is equal to 2, and C11 is a positive of M11. So M11, because of this convention sign, as you start with positive, negative, and then positive again, plus 1, positive 1 times positive M13. So you have 2. You pick this entry, delete the corresponding column and the corresponding row, and you get -1, -2, 1, -2, plus 1, right, times the M13. So M13, you pick this entry, delete the corresponding row column, delete the corresponding row, and you get the determinant of the form 0, -1, 3, +1. All right. So you have this is equal to 2 times negative 1 times -2 is +2 minus -2 plus, right, so 1 times 0 is 0 minus -3, which is +3. So you got 2 times 4 plus 3 equal to 11. So the determinant of A is equal to -7 and the determinant of B is equal to +7. So again, let me delete all of this calculation. I just need the result for the explanation. So equal to 11. Now next we need to calculate the the determinant of the product A times B. So the product of A times B is going to be, so A times B is 1, -2, 2, 0, 3, 2, 1, 0, 1 times matrix B, 2, 0, 1, 0, -1, -2, 3, 1, -2. And if you do the calculations correctly, so I'm going to skip all the formality and give the answer of the product to be 8, 4, 1, 6, -1, -10, 5, 1, -1. And the determinant of this product A times B, or the determinant of the matrix 8, 4, 1, 6, -1, -10, 5, 1, -1 is going to be equal to -77. So I'm going to again skip the formality and just give you the answer. So I just want to focus on the idea of the determinant of a matrix product, right? So if you look more carefully, you can see that the determinant of the product is equal to the product of the determinant. Right? So that is the determinant of the product equal to the determinant of A times the determinant of B. So you can say that the determinant of a product is equal to product of determinant. Right. And we're going to put that in the following theorem, that here, if A and B are square matrices, of the same side. Then the determinant of A times B is equal to the determinant of A times the determinant of B. All right, again, the determinant of the product is the product of determinants. Okay, now we're going to see that relationship again in the next example. This is a lot easier calculation because it's just a 2 by 2 matrices. So the determinant of A is equal to 3, 1, 2, 1, or this is 3 minus 2 equal to 1. And the determinant of B is negative 1, 3, 5, 8, or this is equal to negative 8 minus 15 is equal to negative 23. And the product A times B, right? So you have these two matrices, the product result in the matrix of the form 2, 17, 3, 14. And the determinant of the product is that of 2, 17, 3, 14. You have 2 times 14 minus 3 times 17. And if we do do the calculation correctly, you have 28 minus 41 is equal to negative 23. So again, we just verify that the determinant of A times B is equal to the determinant of A times the determinant of B. So we can say that for the determinant of a product, that the determinant of a product is product of determinants. However, you cannot say that for the case of sum of two matrices. So let's do the calculations on that to verify that the determinant of A plus B is not equal to the determinant of A plus the determinant of B. All right, so again, the determinant of A is equal to, so 1, 2, 2, 5 here is equal to 5 minus 4 is equal to 1. The determinant of B is that of 3, 1, 3, 1, 3. Or this is 9 minus 1 equal to 8. And the determinant of A plus B is that of, so 4, 3, 3, 8. Well, this is 32 minus 9 equal to 23. So clearly, the determinant of A plus B is different from the determinant of A plus the determinant of B. So you have to be careful when you come to this type of relationship between the determinant of a sum or the determinant of a product. So the determinant of the product is product of the determinant, which is good for us. Now, the next properties that I'm going to write down is the determinant of a scalar multiplications. Right. So if A is a n by n matrix, and K is a real constant, then the determinant of K times A is equal to K to the power n, right, where n is the sign or the dimensions of the row or columns, times the determinant of A itself. Right. So let's verify this formula in the following example. So given the matrix is a 2 by 2 matrix, again, negative 1, 2, 3, 4, and K is equal to 2. Now you want to calculate Ka and verify that K times A is equal to K to the power n times the determinant of A. All right, so do K times A. So K is equal to 2. A is negative 1, 2, 3, 4 equal to negative 2, 4, 6, 8. All right, And then you find the determinant of this scalar multiple. So determinant of Ka time equal to -2, 4, 6a. So -2 times a minus 4 times 6. Got -16 minus 24 equal to -40. Now we need to verify, right? So we get determinant of k times a already. Now on the right hand side, we need to do k squared for n equal to 2 again in this case, because the matrix A is a 2 by 2 matrix. Times the determinant of A. So the determinant of A is equal to -1, 2, 3, 4. Well, this is -1 times 4 minus 2 times 3, or -4 minus 6 equal to -10. So the right-hand side of the formula right here is k to the power n times determinant of A. And so k to the power n times the determinant of A, given that k is equal to 2, and is also equal to 2 because it's the 2 by 2 matrix, times the determinant of A, which is calculate, which is -10. So this is 4 times -10 equal to -40, and therefore equal to the determinant of k times A. So we've just verified that the formula we get is true in this case. Or it's true in general, for any square matrix and for any real constant k. In the next example, we're going to move on to a 3 by 3 matrix. We're going to find the determinant of A and the determinant of B. For B is a constant multiple of A, or B is equal to 2 times A. So the determinant of A is going to be 3, 4, 5, 2, 3, 6, 1, 0, 5. I'm going to choose the last row to work with because I have a 0 in the last row, so which make my calculations a lot easier. So it's going to be A31 times C31 plus A32 times C32 plus A33 times C33. This entry is going to be equal to 0 because A32 is a 0 entry. So for A31, you get A31 is equal to 1 times C31. Right? So let's look at the sign for the minors. So plus, minus, plus. So this is positive of M31 plus A33, which is equal to 5 times C33. So this is positive, negative, positive. So this is positive of M33. So M31 is equal to 1. So 1 times. Right, so we're going to choose this entry, delete the corresponding column and the corresponding row. You're left with just 4, 5, 3, 6 plus 5 times M33. So choose this entry, delete the corresponding column and the corresponding row. You're left with the entry of 3, 4, 2, 3. All right, so you get this is equal to 24 minus 15 plus 5 times 9 minus 8, or this is 9 plus 5 equal to 14. Now for the matrix B, we know that B is equal to 2 times A. So therefore, the determinant of B going to be equal to K, in this case, equal to 2. Right, so 2. Or this is, let me be careful here. So, or you'll find the determinant of 2A, right? So K in this case is equal to 2. The matrix A is a 3 by 3 matrix, so n is equal to 3 times the determinant of A, and the determinant of A we just got, which is 14. So this is A times 14, or this is equal to 112. All right, so that's how you calculate the determinant of a constant multiple of a matrix. Now moving on to the next properties. Right, so in this properties, we're going to look at the conditions such that we can identify if a matrix is invertible or not. So a square matrix, A is invertible if and only if the determinant of A is different from 0. Okay, so that's the conditions that we going to carry to see if matrix is if a matrix has an invertible matrix or not. Okay, so find the following determinant. Find the determinant of the following matrix. So I have determinant of A. It's going to be 1, 2, 3, 1, 0, 1, 2, 4, 6. And I'm going to use the second row to work with. So for the second row, I get A21 times C21 plus A22 times C22 plus A23 times C23. Right, I get that A22 is a 0. So this is going to be equal to 0. So we don't have to calculate anything. Now A21 is equal to 1. And we're going to see the corresponding minor of this cofactor. So C21, right? So plus minus. So this is negative of M21 plus A23 is also equal to 1. And let's say the corresponding sign of C23. So plus minus plus minus. So this is minus M23. So 1 times negative M21, so it's negative of the determinant. So M21, we choose this entry, delist the corresponding row, and the corresponding column, we left with the entry of 2, 3, 4, 6, minus M23. Right, so we're going to choose this entry, delete the corresponding column and the corresponding row. You're left with the entry of 1, 2, 2, 4. And here the calculation becomes negative of 12 minus 12 minus 4 minus 4. So the determinant is equal to 0. And when the determinant equal to 0, you can say that the determinant, so the matrix is singular or it has no invertible matrix. So in a way, this particular statement can be negated. And so that means that if the determinant is equal to 0, the square matrix is non-invertible. So that's how you negate it. Now, similar questions here determine if each matrix has an inverse or not. So again, you need to find the determinant of each matrix and identify if a determinant is equal to 0 or not. If it's equal to 0, then the matrix is singular or it has no invertible matrix. If the determinant is different from 0, then the matrix is non-singular and it has an invertible matrix. So for matrix A, I'm going to do the determinant here. So the determinant is 0, 2, negative 1, 3, negative 2, 1, 3, 2, negative 1. All right. And if you notice one thing for this matrix A, that let me call this column 1, column 2, and column 3. The second column and the third column are multiple of one another. And based on one of the conditions that we learned in the last lecture, if that is the case, if one column is a multiple of another column, the determinant is automatically equal to 0. So therefore, you, without doing further calculation, you can claim that this matrix, the determinant of this matrix is equal to 0. So therefore, A is non-invertible. So that means you cannot find an invertible matrix for A. Now for the matrix B, you have the determinant 0, 2, -1, 3, -2, 1, and then 3, 2, +1. And if you do the calculations, you get, so I'm gonna pick the first row here to do with the calculations. So A11 times C11 plus A12 times C12 plus A13 times C13. Okay. And this calculations, this calculation is going to be equal to 0 because A11 is equal to 0. Right. Now, A12, C12, A13, C13, we need to do the calculations. Let's take a look at the side for C12, compare with the minors. So plus, minus. So here you get A12 times negative of AM12 plus A13 times C13 should be positive. So positive, negative, positive times positive M13. So A12 is equal to 2 or -2 for that matter, because you have a negative in front, times the determinant of, pick this entry, delete the corresponding row and the corresponding column, and you're left with 3, 1, 3, 1. Plus A13 is -1. So you pick this entry, delete the corresponding column and the corresponding row. You're left with 3, -2, 3, +2. And if you do the calculations correctly, you get -12, which is different from 0. And you see that, and you can say that B has an invertible matrix, or B is invertible. So this implies that B is invertible. All right. Now, if you can find the inverse of a matrix, what is the determinant of the inverse of the matrix? So if A is invertible, then the determinant of the inverse matrix is equal to 1 over the determinant of the original matrix. Okay, so you have this kind of operations because the determinant of a matrix is a number, so you can have 1 over that number. However, when you do the matrix, inverse matrix, right, so A inverse, this is not going to be the same at 1 over A, right? So there's no such operations. So be careful between the two situations. Now we're going to quickly prove this determinant of inverse of a matrix. Let's see what we got here. So suppose that A is invertible, then you can have that A times A inverse is equal to the identity matrix of the same side of A. then it follows that the determinant of A inverse times A is equal to the determinant of the identity matrix. Basically, you just take the determinant on both sides of this equation, right? And the determinant of the identity matrix, right? So let's see the identity matrix here. One, so one, 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 everywhere was a zero. So this is the diagonal matrix. So the determinant of diagonal matrix is just the product of all the entries on the main diagonal. So everything multiplied together give you one. On the other hand, the determinant of a product is equal to product of determinant. That's what we learned earlier in this lecture. And of course, this is equal to one as well, right? Therefore, you can say that the determinant of A inverse is equal to 1 over the determinant of A. Right? You get that by dividing both sides of the equation by the determinant of A. So basically, you just prove that the determinant of A inverse is equal to 1 over the determinant of A, given that A is an invertible matrix. In the next theorem, we have the following conditions that for non-singular matrix, these conditions are equivalent to one another. So the first one is that, okay, so the setup is that A is the square matrix, n by n matrix. Then the statement below are equivalent to one another. That is the determinant of A. Sorry, let me do this first. So A is invertible. The equivalent to that is that the determinant of A is different from 0. And when A is invertible or determinant of A different from 0, you can have that AX equal to B is has a unique solution for every column, matrix B of the form of the size, sorry, n by 1. Is also equivalent to the statement that the homogeneous system has only trivial solutions. So that is x equal to a 0 zero matrix, zero column matrix, to be clear on that. The next one is that A is row equivalent to the identity matrix. And that the last two is not going to be a concern for us, but A can be written as the product of elementary matrices. Right. So the last two basically, the last two statement basically does not concern us in this particular course. So gonna get rid of that. All right. So when you have a square matrix, if A is invertible, then determinant of A is different from 0. The matrix equation AX equal to B has a unique solutions, and the homogeneous system has only trivial solutions. Right? All of these four statements are equivalent to one another. The last two is just part of the theorem, but not going to be a concern for us. Now, moving on to the last part of the lecture, we're going to find the determinant of transpose of a matrix. Right. So the determinant of a transpose of a matrix. Right? So for any square matrix A, we get that the determinant of A transpose is equal to the determinant of the original matrix itself. Right. And we're going to perform a quick calculation here to verify that particular statement. All right, so I'm going to calculate the determinant of A and the determinant of transpose. Right, so determinant of A. So determinant of A is equal to determinant of 3, 1, -2, 2, 0, 0, -4, -1, 5. So this is equal to, I'm going to choose the second row to work with. Right, so A21, C21 plus A22, C22 plus A23, C23. So this is equal to 0. This is equal to 0 because the entry A22 and A23 are zeros. Right? Now we check the sign of the corresponding cofactor. So plus, minus. So this is going to be, right, so A21 times negative of M21. Well, this is going to be -2 times the determinant of, so pick this entry, delete the corresponding row and the corresponding column. You're left with 1, -2, -1, 5. Well, this is -2 times 5 minus 2. All you get, this is equal to -6. So that's the determinant of A. Now you're going to find A transpose. So A transpose is going to be 3, 1, -2. So for transpose, rows become columns, columns become row. So 2, 0, 0, and -4, -1, 5. All right. So to calculate the determinant of this particular matrix, again, I'm going to choose the second column to work with because it's carried the most zero here. So A12 times C12 plus A22 times C22 plus A32 times C32. So this 2 is going to be equal to 0 because the entry A22 and A32 are equal to 0. So you got A12 times C12, and we're going to test the sign, check the sign of this corresponding to the minus. So plus, minus. So you have 2 times negative M12 or -2 times. I'm going to check this 2, delete the corresponding row and the corresponding column. You're left with the entry 1, -1, -2, 5. And the determinant becomes so -2 times 5 minus 2 is equal to -6 as well. So therefore, we just verify that the determinant of A is equal to the determinant of the transpose itself. All right, so that's it for me for this lecture. And in this lecture, we look at multiple properties of the determinant. Right? We look at the properties of determinant of matrix product, the scalar multiples. We look at the properties where we check if a matrix has an invertible matrix or not. Is an invertible matrix or has an inverse matrix or not, based on the fact that if the determinant of A is different from 0, then A is invertible. And if A is invertible, then you have the determinant to be different from 0. We look at the formula where you can calculate the determinant of the inverse of a matrix, right? Given A is an invertible matrix. We have this following equivalent conditions as well. If A is invertible, then the determinant of A is different from 0, or n, uh, the matrix equation AX equal to B has unique solutions, and the homogeneous system has only trivial solutions. And then at the end, we look at the properties that the determinant of A transpose is equal to the determinant of A. So that's it for me. Please let me know if you have any questions. Thank you.